So the law of cosines is one of the first few trigonometric identities that we're going to be studying in this class. It's basically going to help us solve a triangle when given different pieces of information, like you did in geometry. So if we agree on what's called the usual labeling of a triangle, all of what I'm talking about for the law of cosines and then the law of sines next time will make sense. So the usual labeling of a triangle, if we let this be side or angle A, angle B, and angle C denoted by uppercase letters, sometimes denoted with also like the little angle symbol in front of them, but capital letters are angles, then we can also understand that the side length that is A is across, is opposite of A. So again, opposite of angle capital A is side length lowercase a, which means this is side length B and this is side length C. Again, they are opposites from their angles. Now, the law of cosine is used to find non-right triangles. So when we have a right triangle, we can use Pythagorean theorem. But when we have a non-right triangle, meaning there's no right angle, no 90-degree angle, we can't use Pythagoras' theorem anymore. So we turn to the law of cosines, because we sometimes call the law of cosines generalized Pythagorean theorem, because it's going to be able to be used for all triangles, so it's generalized. So if we let triangle ABC be any triangle with sides and angles labeled in the usual way, which we just talked about, then the law of cosines gives us three formulas, one for each of the sides depending on what we know. So if we know, or if we want to find side length A, all we would need to do that is side length B, side length C, and again B and C, and then the angle A. If we wanted to know side length B, all we would need is A and C again, and angle B. If we wanted to know angle C, you can kind of tell all the variables shift to take over. We need A and B to find cosine of angle C. So the way to think about this and to help you memorize these formulas is you have an angle theta or a side that is opposite of angle theta. Then to find that opposite side length, you would do the opposite side length squared equal to one of the adjacent side lengths squared times plus, I don't know why it says times, this is a plus one of the adjacent side length squares minus 2 times the adjacent side length times the adjacent side length times cosine of that theta. Again, that theta has to be opposite of the side length. So these are just three formulas that we're going to be able to use to solve triangles. Again, solving triangles is finding all of the values of the sides and all of the values of the angles. Now, this is the proof of the law of cosines. I probably skipped this during your class, but it's actually pretty interesting, and proofs themselves are pretty interesting. Basically, to derive or to prove the law of cosines, we start by looking at the three types of angles we might have. You have your right angle, you have an acute angle A, or you have an obtuse angle A. In all three scenarios, if we define cosine of theta, we'll do A, so cosine of A to be the x value divided by r, the radius of a unit circle, and sine to be y divided by r, just like we did on a unit circle. And we can define the radius of the circle, the r, to be side length B, because if you notice, if this was a circle, that would be the radius. It would still be the radius, and it would still be the radius. Okay, so if side length is B, then that means the x value to get to B is x, and the y value is y. On that point, that creates angle C. So we can define cosine of A to be x divided by B, and sine of A to be y divided by B. If we solve for x and y, like you just multiply by b, then you have x equal to b times the cosine of A, and y equal to the b times the cosine of A. Sine of A, sorry. If we notice that A is the distance from C to B, so from angle C to angle B, that's always defined as side length A, then the distance formula allows me to say that A is equal to the square root of x minus c squared plus y minus 0 squared. Again, that's the distance formula. Okay, so we start deriving. To go from here to here, I squared both sides. And then I took the idea that x and y we already defined as b cosine of A and b sine of A. So I just plugged that in for x and y. And so we just square these things. And we haven't squared a sine or cosine formula yet, so when we get into the trig identities, wow, I just stuttered over those words, this will make more sense, but this will be b squared cosine squared of a minus 2bc cosine of a plus c squared. That's all of this squared. Yikes. And then this is b squared sine squared of a. Okay, if you notice these two pieces right here, they both have a b squared. So I'm going to factor out the b squared and have cosine squared a and sine squared a left in the center. Then I have negative 2bc cosine of a and c squared. This is starting to kind of look like my law of cosines. There's one trig identity we haven't really talked about yet, but cosine squared of theta plus sine squared of theta is equal to 1. So all of this is 1, and so b squared times 1 is just b squared. And voila, we've already arrived at our law of cosines. So it combines the trigonometry of cosine and sine for the general triangle, as well as geometry distance formula, aka Pythagorean theorems, generalized for all types of angles. Pretty cool. You don't need to know how to prove it, but what you do need to know is how to use it. So if we're given this problem, yes, I already showed you the answer, we're going to be able to solve triangles that are side angle side and side 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 using the law of cosines. Okay, so those are the two scenarios, the two givens that we'll be able to use the law of cosines. If we're given that A equals 11, B equals 5, and capital C equals 20 degrees, we know that we're talking about side length A, side length B, and angle C. Okay, cool. Meaning I need to know side length C. So I can use the C version of the law of cosines and plug in everything I know and be able to compute that C is about 6.5. Now, I highly recommend storing this value when you're solving triangles. So to do that on your calculator, you'd press the button above on to store, and then just pick whatever letter you solve for. This is important because rounding sometimes loses the sensitivity for the numbers. So I would always just store the value. Okay, next up, we need to define angle A and angle B. So if we look at one of the versions of the law of cosines, I'm particularly finding A. You could find B and use the B version of it. I derived this formula before I plugged things in, but you don't have to do that. From here, you could plug in everything you know and then just start solving for A, but I chose to do it, derive the formula for it because it's just easier for me. So what I did is I subtracted b squared and c squared to both sides, and then I divided by 2bc to get the cosine of A by itself. And then to get the angle A out of that cosine function, I have to take the inverse cosine of both sides. These would cancel out. So we want the inverse cosine of a squared minus b squared minus c squared, all divided by negative 2bc. And so I plug in those values. Again, we just stored this value c in our calculator. So instead of typing 6.5 in there, I can just type alpha c and be able to use a more accurate number. And the calculator is going to pop out to us that angle A is approximately 144.8 degrees. Now, some people are probably going to thinking, man, Ms. Quigley, we got to do that again. Well, remember, we now know 2 of the 3 side lengths. Use geometry again to figure out what the side lengths, the angles. Use geometry to figure out what the other angle is. We know that a triangle has 180 degrees, so if we take away angle A and angle C, which we already know, the only thing angle B can be is 15.2 degrees. So we found the 3 missing pieces, and to solve the whole triangle, we would have all 6 pieces, capital A, lowercase a, so angle A and side length, angle B and side length B, angle C and side length C, for that allows us to solve the triangle. So let's do this one together. This is going to be an example that we spend a little bit more time on. So it says solve triangle ABC if A equals 9, B equals 7, and C equals 5. We're given 3 sides, which means I can use the law of cosines to be able to solve this triangle. Here's going to be my triangle. We'll label this A, which means this is 9, B, which means this is 7, and C, which means this is 5. Doesn't matter where you put A, B, and C as long as the correct side length is across from it. In fact, if you're looking at my notes version of this versus what I'm doing on this video, they're actually labeled slightly differently. As long as the letters line up correctly, you're fine. Okay, it doesn't really matter what you do first. I'm going to solve for a because alphabetical order, which means I know a squared, I know b squared, I know c squared, so I know 2bc, and I want to find that angle A. Fabulous. This time I'm going to plug in the values before I use my calculator, or before I derive the formula, just because I think that's what most of you guys will do. So this is going to be 9 squared equal to 7 squared plus 5 squared minus 2 times 7 times 5 times the cosine of A, which I don't know yet, and that's what I'm trying to find. Cool. Let's move some things around. This is going to be 9 squared minus 7 squared minus 5 squared equal to negative 2 times 7 times 5 times the cosine of A. And then we're going to divide by negative 2 7 times 5 to get the cosine of A by itself. So we're going to have 9 squared minus 7 squared minus 5 squared, all divided by negative 2 times 7 times 5 equal to the cosine of A. And to get that A by itself, we're going to take the inverse cosine of both sides. I did not leave myself enough room. That'll be fine. I'll just squeeze it in here. And at this point, I can throw that into a calculator, and when I do, I get that the value of A is going to be approximately 95.7 degrees. All right, so I have angle A. I just need angle B and angle C. My brain is thinking that I'll have to do something with the law of cosines one more time, and then I can just use geometry. So let's solve for angle B. The B version, the one that uses angle B, is going to be b squared equal to a squared plus c squared minus 2ac times the cosine of B. So if we plug everything in, this is going to be 7 squared equal to 9 squared plus 5 squared minus 2 times A times C times the cosine of B, which we don't know. We want that angle B. Again, you'd rearrange this equation to get B by itself. So you'd subtract 9 squared and 5 squared from both sides, then divide by negative 2 times 9 times 5 to get that cosine of B isolated. And then to really get the B by itself out of that cosine function, you would need to take the inverse cosine of 7 squared minus 9 squared minus 5 squared all over negative 2 times 9 times 5, which is a calculator question. And when you chunk that into a calculator and calculate, you'd get that B is approximately 50.7 degrees. Cool. I've got two parts. I've got angle A and I've got angle B. To finish solving this triangle, all I need to do is find angle C. But to do that, all I have to use is a little bit of geometry. Remember that all triangles have to add up to 180. So if I'm finding angle C, all I need to do is take 180 degrees and subtract angle A and subtract angle B. And that's like super easy to do. So we're going to do 180 degrees minus 95.7 degrees minus 50.7 degrees. And we'd get that angle C is 33.6 degrees. And so then we solve for all parts of this triangle. We have angle A, angle B, angle C, side length A, side length B, side length C. So if we put it all together into one, angle A is 95.7 degrees, side length A is 9. Angle B is 50.7 degrees, side length B is 7. Angle C is 33.6 degrees, and side length C is 5. So we've solved the triangle because we found all parts of it. Now, something else that comes from the law of cosines means that we also know new formulas for triangle area. Remember, if you think back to just regular geometry, if we found the area of a triangle, it would be 1/2 base times height. But if we had a non-right triangle, it still looks like a right triangle, let me draw it a little bit better. If we were pretend that's a triangle. We wouldn't use base times height because there is no height. We'd use what's called the altitude, which is essentially the height at the highest point of the triangle. 1/2 base times altitude. Okay, but due to the law of cosines, and the proof is in the textbook, I didn't include it in these notes, we know that each triangle has base C and altitude y equals b sine of A. Again, the proof for this is in the textbook if you're interested. This means that we have 3 new formulas for area based on what we were given. If we're given 2 side lengths and the angle, so side angle side, we can find the area of that triangle using these formulas. 1/2 BC sine of A, 1/2 AC sine of B, and 1/2 AB sine of C. So let's see. It says we want to find the area of a regular octagon inscribed inside a circle of radius 9 inches. So here's my circle. An octagon has 8 sides, and a regular octagon, all 8 sides are the same length. So 1, 2, 3, 4, 5, 6, 7, 8. And we're just going to pretend that those are all the same length. I am an artist. And this circle has a radius of 9 centimeters. And I'm going to draw it specifically here. This is 9 centimeters. That's all the information we're given, and we want to find the area of this polygon. Okay, so some information we have just to kind of make sense of this is we have a side length of 9 centimeters. Oh, but check it out. This is also a radius, so this is also 9 centimeters. We have 2 sides. We also technically have this angle. A full circle is 360 degrees. So angle C here is going to be 360 degrees divided by 8 pieces. Because if we count and make a bunch of pizza pie slices, there's 8 of them. So each little pizza pie slice is 45 degrees. Okay, so since I have side angle side, I know I can use the area formula, but I'm only going to be finding the area of this little slice, so I'm going to call it A slice. Area of the slice. It's 1/2, if we write down the formula, 1/2 A times B times the sine of angle C. So if we fill that in, 1/2 9 times 9 times the sine of 45. Now, sine of 45 should look familiar to you. Sine of 45 is something we should know based on our hand trick, so we could actually find an exact value for this. 9 times 9 is 81, so this is 81 divided by 2. And the sine of 45 is square root of 2 over 2. So the area of this slice is 81 square root of 2 over 4. That's the exact value, which if we were just going to round is approximately 28.6. What are we measuring in? Centimeters. Okay, so that's really cool. We needed that area of a slice, but that's not what we wanted. We want an area of the entire octagon. So a octagon is just 8 of those slices. We're going to do 8 times that 28.6, or, because that's an approximate value, we're going to do 8 times 81 square root of 2 over 4. The exact value here, if we were to be particular and use the exact value, we'd have 162 times the square root of 2, but really that comes out to approximately 229. Oh, we're not measuring in centimeters. This is inches. Wild. Let me go back and fix all of that. That's embarrassing. Measuring in inches. fix that. We again found our area of the entire shape because we found an area of a slice. We had side angle side, and we're able to use the new area formula to find the area of this octagon. Another important thing that we're going to have from the law of cosines is called Hudsons Formula. This is going to help us when we have side, side, side. It's going to help us find the area of a triangle when we don't have any of the angles. It says let A, B, and C be the sides of triangle ABC as per usual. Let S denote what's called the semi-perimeter. Semi means half, so it makes sense that the semi-perimeter is literally half of what is normally the perimeter, which means we just like add up all the sides. So the semi-perimeter is A plus B plus C divided by 2, half of the perimeter. Then the area of triangle ABC is given by the formula. Here, this is called Hudsons Formula. Area of the triangle is the square root of the semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the, you guessed it, semi-perimeter minus C. That's Hudsons Formula. So if we aren't given any angle measurements and still asked for the area, we can use this formula for all 3 side lengths. Now this is the proof for Hudsons Formula. I'm not going to go through it because it's pretty complicated, but if you're interested in finding proofs, if you're interested in this sort of stuff, this again is out of your textbook and is actually pretty interesting. But what I need you to be able to do is use Hudsons Formula to find the area of a triangle. We know we need to use Hudsons Formula again because we were given 3 side lengths, no angle, and still asked for the area. So if we notice that, we know we're going to use Hudsons Formula. We first need the semi-perimeter. So the semi-perimeter here is going to be 13 plus 15 plus 18 divided by 2. Therefore, our semi-perimeter is 23. Cool. Great, now I have everything I need to fill in the area of a triangle formula for a Hudsons Formula. We're going to be doing 23 times 23 minus A, which is 13, times 23 minus B, which is 15. And then, yep, you guessed it, 23 minus 18. That is something we can throw into a calculator. If we were doing this by hand, you'd have, again, like SAT, doing it by hand, 23 times 10 times 8 times 5, which is the square root of 9,200. We'd reduce out all of our formulas. We'd get 20 times the square root of 23. But since we have a calculator and I'm not asking you for exact value, you can round this to about 96 square units. That's the area of that triangle with those particular side lengths. Again, I didn't need a base and a height. All I needed was all of those side lengths. Now, last but not least, some application in the real world. Let's say we are the turf master for a baseball diamond. The bases on a baseball diamond are 90 feet apart, and the front edge of the pitcher's rubber is 60.5 feet from the back corner of home plate. Find the distance from center of the front edge of the pitcher's rubber to the far corner of first base. So this is not a 90-degree angle, so I can't just use Pythagorean theorem. So I'm just going to draw this triangle again out here just because I just need to. It's kind of too small. So this is angle C, but angle C is 45 degrees. They've named this angle A, this one angle B. We don't know side length C, but we do know that side length A is 60.5 feet and side length B is 90 feet. That's one from the picture and from the description here. Okay, cool. We want to know how far it is from the pitcher's rubber to the far corner of first base. So we want side length C. Well, I know side length A and B and angle C. So if you remember, that's everything I needed to plug in and figure out using law of cosines starting with the c squared. C squared is equal to a squared plus b squared minus 2ab times the cosine of angle C. So if we plug in what we know, we're looking for C. We know A is 60.5. We know B is 90. Again, we know A, wow, I made that so small. Times the cosine of 45. Again, we know the cosine of 45 because it's part of our hand trick, but we can just use a calculator on this one. So if we throw all of that into a calculator, making sure a calculator is in degrees, we'd get that c squared is equal to 4,059.86 approximately. So we also can take the square root of that. We know that c is approximately 63.72 feet. So that's about how long it is from the pitcher's rubber to first base. A little real world usage of the law of cosines.